is Kristine Bauer from the University of Calgary, who will speak to us about categorical differentiation of homotopy functors and applications. Kristine.
Thank you very much. I'd like to thank the organizers for the chance to speak at this conference. I very much appreciate the invitation. Martin, could I ask you a favor? Would you mind interrupting me and telling me when it's 20 minutes that have passed?
Glad to do that.
Thank you. Okay, so I'm going to talk about categorical differentiation of homotopy functors. In this case, I'm talking both about categorical differentiation in the sense of Luke-Cockett-Seeley's differential categories, and also differentiation in the sense that we tend to think about it in topology with Goodwilly's functor calculus. So in the original paper that introduces categorical differentiation in terms of Cartesian differential categories, Luke-Cockett and Seeley say that over the past few centuries, one of the most fundamental concepts in all of mathematics has been differentiation. And then they proceed to show how differentiation is so fundamental that it shows up in places that we might not have thought about it in the past. So I want to give you a little bit of an introduction to what this is. And this is related to the tangent categories that Jeff Crutwell spoke about this morning. The Cartesian differential categories that I'll talk about are kind of like trivial tangent categories in some sense, where the tangent structure is trivial, but they are closely related to one another. Okay, so here's a motivating example of what it means to be a Cartesian differential category. So let's look at the category smooth, whose objects are the natural numbers, or I might think about these for each natural number. I'm really secretly thinking about this as Rn. And the morphisms are smooth maps from Rn to Rm. Then we all teach our undergraduate students that you can differentiate in this category. I'll denote the Jacobian by capital DF. So if I have a map from Rn to Rm, I can form its Jacobian. And this gives rise to the directional derivative just by taking the product, the matrix vector product of the Jacobian evaluated at a point A in the direction V. So what that means is that I'm really thinking about this thing that I've denoted nabla f as a new function from Rn cross Rn to Rm. And that's kind of the basics of what I want to start with for what I want the derivative to do. And first we'll note that this derivative, the directional derivative, satisfies all these really, really nice properties. That nabla that I just showed you is a linear operator. If I add f and g, then I just differentiate by taking the derivative of each one of them and adding them together. In the direction variable, the v, this is a linear function. There's a chain rule. The Jacobian of the identity function is the identity matrix. Derivatives commute with products. In other words, if I so this is not the product rule that we teach in Calculus 1, but rather if I have two functions f from Rn to Rm and g from Rn, say Rn prime to Rm prime, then the derivative commutes with whatever you want to denote the new function fg that goes from Rn cross Rn prime to Rm cross Rm prime. The derivative just does that component-wise, just as we define the function component-wise. And linear functions have a particularly simple derivative, and the mixed partials agree. Okay, so these nice properties that I have listed, in fact, determine what the directional derivative had to be. If I have any function that satisfies all of these properties, then it was the directional derivative. And that's kind of the idea behind Cartesian differential categories. So a Cartesian differential category is a Cartesian left additive category. So you can think about that as a category in which each of the objects has some kind of monoidal structure or abelian group structure if you prefer. So a Cartesian left additive category which has a differential operator that takes a map from x to y and sends it to something like the directional derivative, satisfying these 8 properties. Well, these 8 properties are exactly the formulation of the properties that I showed you on the previous slide, just written in equational terms instead of with their descriptions, like here's the chain rule, for example. Okay. So a Cartesian left additive category that has a differential operator that satisfies these 8 properties is called a Cartesian differential category. And the idea is that now I no longer have to limit myself to looking at vector spaces Rn and smooth maps between them, or indeed any other differential geometric object. I can look at all kinds of different examples of things that might have differentiation and get lots of applications all over the place. And so when Blue-Cockett and Seeley said that differentiation was fundamental, here's part of what they meant. The applications of categorical differentiation can be found in synthetic differential geometry and differential geometry. So Jeff told us a little bit about this morning. I probably should have added Ben McAdam and Matthew Burke to this list, and some of the applications that we've heard about today to Lie groupoids would fall into this category. Linear logic and computer science has examples of categorical differentiation. There are applications to game theory, machine learning, and today I'm going to tell you about an application to homotopy theory that me and some of my co-authors have worked on. Okay. So let me back up and tell you a little bit about functor calculus, which is where the homotopy theory comes in. So let F from C to D be a homotopy functor of model categories. Okay, if you don't know what a model category is, or if you're an infinity category person who just doesn't want to talk about model categories, I really only have 2 things in mind. So you can either think about C and D are categories of chain complexes of an abelian category. Or you can think about C and D are the category of topological spaces, or its related category of the stable category of spectra. Okay, so depending upon who you are, just keep those examples in mind. Well, then a functor is excisive if it takes a homotopy push-out diagram to a homotopy pullback diagram. So in particular, I have a favorite push-out diagram. It's the one that produces the coproduct. And if my functor is also reduced, in other words, it takes the 1-point space or the initial object, 0 object to itself, then what this says is that a functor is excisive if it takes the coproduct diagram to a product diagram. So this required me to say one more thing, which is that F takes the 0 object to the 0 object. Well, functor calculus takes any functor, homotopy functor of model categories, and produces a whole tower of approximations that are kind of like the Taylor series. And the idea is that the nth part of this tower is going to be the best n-excisive approximation. N-excisive just means that I take an n+1 cubical push-out diagram to an n+1 cubical pullback diagram. And then that thing that I had about this property that looks kind of like linearization, where I take a coproduct to a product, well, that's going to be more appropriate for the fiber of these maps Qn between the nth excisive approximation and the n-1st excisive approximation. And in particular, D1, which fits as the fiber of Q1, satisfies exactly that property. It is linear, it takes coproducts to products. And in fact, we say that D1F is the linearization of F. Well, just like differentiation is very fundamental, in homotopy theory, functor calculus has become very fundamental. So you can use functor calculus for a variety of different things. So in particular, you get insight into hard theories by looking at relatively easy theories. So if you have a functor like K-theory that's very difficult to compute, you might be able to compute the layers Dn, or maybe even the polynomial approximations Pn, as was done by Dundas, Goodwillie, and McCarthy. In fact, this is one way of formulating what the Dundas trace map is. You might be able to derive interesting new theories. Homology theories in particular are known to be linear, from familiar functors. So this has been done with some frequency to forgetful functors of various types. In particular, Schweda noticed that this is one way to describe topological Andre-Quillen homology. And finally, you might be able to enumerate or classify functors of a particular type, in particular, the polynomial functors. And this was done by Aron and Ching. So all of these are applications of what functor calculus can do for you. And what I want to show you now is that, in fact, one of the reasons functor calculus is so useful is because it is exactly an example of a place where categorical differentiation arises. So a few years ago, along with my co-authors Brenda Johnson, Christina Osborne, Emily Reel, and Amelia Tebbe, we showed that the homotopy category of abelian categories is a Cartesian differential category. So this is a category whose objects are abelian categories, whose functors are any maps between abelian categories. And we took, for any functor of abelian categories, the directional derivative to be, okay, so this is a little tricky. So D1, remember, is the linearization of a functor. So we take the composite of F together with the functor A direct sum blank. Okay, so if you just add A to an object. If you linearize that composite and evaluate at V, what you have done is produced the directional derivative of F at A in the direction of V. And this satisfies those 8 properties that we talked about, at least up to chain homotopy equivalence. So in my homotopy category of abelian categories, I will rig things to make it so that functors always land in chain complexes. And so I'm able to talk about these things being homotopy functors using chain homotopy equivalence. Okay. So when we started the project that created this theorem, what we were really after was a higher order version of the chain rule. So in the original paper that studies abelian functor calculus is written by Brenda Johnson and Randy McCarthy, and they already knew how to take what now we would call the first directional derivative of a composite f and g. And what we wanted was a higher order version of that. So in regular calculus, the higher order chain rule, or the chain rule for the nth derivative, is called the Fodde-Bruno formula. So how do we take a directional derivative and get a higher directional derivative? Well, you do that by taking your directional derivative and recognizing that that thing is going to be, my directional derivative, nabla f, was a functor of 2 variables. And so I can hold the second variable, I can hold the first variable constant and make this a functor of a single variable by just looking at what happens in the a variable. And then I can iterate. And if I continue doing that, then the nth directional derivative is now a functor of n+1 variables. And what we showed in this same paper, in which we showed that abelian functor calculus is an example of Cartesian differential calculus, Cartesian differential category, is that the nth directional derivative of a composite f and g can be obtained from composites of lower derivatives in the same way that you would expect to have happen in regular calculus. So this Fodde-Bruno formula exists in calculus, multivariable calculus as well. There's a nice account of this in a paper by Huang and Marcantonini and Young. And it looks exactly like this one does, except that replace nabla as the linearization of f of a plus blank with the usual directional derivative that you get from the Jacobian. And what we learned shortly after this is that maybe we should have known this already, that had we taken the categorical approach from the get-go, if we'd understood that we were looking at a Cartesian differential category from the beginning, we might have known that Cockett and Seeley had already looked at Fodde-Bruno formulas and shown that for any category A with products, this has to be a Cartesian left additive category as it was before. Then there's an associated category phi of A. The objects of this associated category are just the monoids in A. And the morphisms in this category are sequences of morphisms, which go, the ith morphism in the sequence will go from A times I to, from times A to B. And these have to be symmetric and additive in the first I variables. And the idea of these morphisms is that that ith thing behaves just like the ith higher derivative. The ith higher derivative is a functor, for us it's a functor, of I plus 1 variables, and it is symmetric and additive in all of the direction variables. So that's exactly what Cockett and Seeley were doing. Composition is a little bit funny. So the composition of f and g, the nth thing in its sequence, looks like the sum over all of the partitions of n, and then this composite. So fk, remember, takes k plus 1 variables. So I will insert g's as written here, where what I've done is each of those i's corresponds to a partition of n. So if I added up all the i's, I would get n. Okay. So the theorem that Cockett and Seeley proved is that phi is a comonad on the category of Cartesian categories, and the coalgebras over phi are precisely the Cartesian differential categories. So let me make this clear now why it is that this recovers what we had noticed about the chain rule. So this functor, so if it turns out that phi is a comonad, that means in particular that there is some functor, which I will not accidentally call nabla, from C to phi C, which on objects is the identity. So this nabla functor just takes nabla of x to x. And maybe I'll denote this with a star to make it clear that I don't mean the first directional derivative. Because on morphisms, what this will do is take a morphism f from x to y and send it to the sequence of morphisms, nabla star f, which is f in the first place, but then it's the first derivative of f, the second derivative of f, f, the third derivative of f, and so on. Okay, so why is it that this recovers the phi de Bruno formula that I showed you before? Well, if I look at what's happening to a composite in the nth part of the sequence, then this is a functor, so it has to be the case that this is nabla f composed with nabla g, oops, sorry, nabla star g, but in the way that I showed you that composition was defined on the slide before, that thing has to be the sum over all nabla kf of nabla I1g through nabla ikg, and then there's always something funny that happens in the zero spot. And this is exactly the phi de Bruno formula that we had noted we had for abelian functor calculus. So it turns out that these things go hand in hand. Okay, well, if you're a topologist or a category theorist or anyone who has seen operad composition before, this should be making you think that something is going on. It made us think that something was going on, and so when we went back and thought about what we knew about operads and abelian functor calculus, we remembered that McCarthy and Manasian had shown that there is indeed an operad that is very similar to the one that we're looking at. So this D1 CRNT, this is kind of another way of saying nabla n t evaluated at S in every place. And McCarthy and Manasian showed that that was an operad. And similarly, Michael Ching has shown that the derivatives of the identity functor of topological spaces form an operad. And all of these are closely related to the operad that we were to the things that we were looking at. So like I said, this thing is really nabla n f evaluated at S in every place. So I will finish by talking about an application that we're hoping for of categorical differentiation in this case. We're really hoping that in fact, these things that I've shown you explain these operad structures that we have seen appear elsewhere in the literature. So how would that work? Okay, well, remember that my nabla functor in this case, because the category of abelian categories is a Cartesian differential category, then I should get a functor from abcat, the Cartesian differential category abcat, to phi of abcat. All right, so we'll call this nabla star. So this is going to take an abelian category A to A. Remember, it's the identity on objects, and I've already showed you what this is going to do on a functor f. This is going to take this to that sequence, nabla star f, of derivatives. But what if we knew a little bit more? ABCAT is, in fact, a bicategory. So remember, this is the homotopy category of abelian categories, and it's a bicategory because it's closely related to the two-category structure of cat itself. So in particular, if f, maybe I want to call this mu, if f was a monoidal functor, then there's a natural transformation from f composed with itself to f. Okay, so this is in case f is a monoid. And I would like it to be the case that nabla star in that case produces a natural transformation from nabla star f like this. Okay. But this one, of course, is the same thing as nabla star f composed with nabla star f.
Kristine,
and
20-minute warning.
Thank you very much. Good. I'm just wrapping up. Okay, and nabla star f, this thing that I've written down here, this is a symmetric sequence of functors because of the fact that in the Fa category, the functors are symmetric and linear in all of the direction variables. So what I have now produced from a monoid f is a monoid of symmetric sequences, and that's otherwise known as an operad. Okay, but in order for, the reason this is a conjecture and not a theorem is because of a number of things. So we know that ABCAT is a bicategory, so Sarah Yackel proved that already. But we don't know that Fa of a bicategory is again a bicategory. So that's something that we're in the process of verifying. I think it's true, but that's part of why this is a conjecture. And then we would need to know that the functor nabla star that you get from the Cockett and Seeley theorem is in fact a homomorphism of bicategories in order to know that the multiplication map was carried to multiplication in ABCAT was carried to multiplication in Fa of ABCAT. Okay, so that's what we're hoping for. All right, and then just to kind of sum up, we hope that this construction recovers the McCarthy-Manasian operad that I showed you before. And then we're hoping that it does quite a bit more, actually. The operad that I told you that Michael Ching had discovered on the derivatives of the identity functor is actually a very powerful operad. It can be used to classify all functors of spaces and spectra. And this was done by Aron and Ching. So what we'd really like to know is that, in fact, we can do the same thing for functors of abelian categories, that we can use this conjectured operad structure to then classify functors of abelian categories. So that's the application that we're hoping for. And if that works, then we can ask, does that in fact recover the unstable case that Aron and Ching have done? And we can do that through the fact that we already know how to kind of think about functors of topological spaces in terms of differential category theory. In that case, it's a tangent category. And that's the relationship to what Jeff was saying this morning, is that we can do that for functors of infinity categories. It turns out that there is a tangent category structure. Okay, so I was going to explain a little bit more about that classification, but I'll skip that. And instead, I'll just thank you for your attention. Thanks again to the organizers. And here are some of the pointers to some of the papers that I referenced in this talk.
All right, let's thank Kristine for a very nice talk.
Thanks.
Do we have questions for her? We have a bit of time for that. Yes, Chef, please do unmute yourself and go ahead.
So this question is about something earlier around the cool later stuff, unfortunately. Right near the beginning, you were talking about the different properties the derivative has. And then I wasn't sure if you were saying something precise there or not. I think it sounded like you said something like all these properties are only satisfied by the derivative. Were you stating some kind of like precise thing there about the derivative that if you have some kind of operation which satisfies these 7 properties, it must be the directional derivative? Or was that just sort of a general statement that it's that the directional derivative satisfies these things and it's nice?
Yeah, maybe I overstepped a little bit. So I did say that I think that these properties actually classify the directional derivative. So I think that if you have an assignment from a function of smooth, a smooth function to another function that satisfies these properties, it is the directional derivative. So I think it determines the derivative. Did I overstep that? You know better than me.
I guess I don't know. I was just talking about this with Jess the other day, actually, and I don't know any result that says that specifically, that something that satisfies those things has to be the directional derivative. So I was wondering if there's some theorem you knew about that said that, or whether yeah.
Okay, I'll withdraw that and just say that the directional derivative does satisfy these 8 properties. So maybe I overstepped in that case. Thanks.
Do we have more questions for Kristine?
Matthias?
Thank you.
Hello, Kristine. Do you think you could go back to the slide, the one just before the Fali-Bruno formula? I'm sorry, it's a basic question about your earlier work.
No problem. Just give me a second. I should have left my slides up because this always takes me a moment. All right, so this is the first time that we stated the Fali-Bruno. Yeah.
The previous one.
Okay.
That one.
Yep.
There, I usually think of the possibility of differentiating something, a morphism, as a property of the morphism. But here in your definition of nabla, it looks like you can do it because A has a monoidal structure. So I guess you could do the same definition for categories equipped with a monoidal structure. Now I guess you cannot really do that, and that's where abelianness play a role. So I wonder whether you could pinpoint where abelianness allows you to say that this is actually differentiation.
Okay. I will tell you that the important property of being an abelian category that made it so that this way of doing things worked really well is that abelian categories have biproducts. So in that formulation that I showed you at the very beginning, so remember that D1's job is to produce a functor that is both reduced and excisive. And in the formulation that I gave you at the beginning of what it meant to be reduced and excisive, I said that a functor which is reduced and excisive has the property that f of x plus y is the same thing as f of x times f of y. Yeah. But if I'm working in abelian categories, these are in fact the same thing. So I could say both that f preserves coproducts and f preserves products. So it's a little bit different than having to take a push out to a pullback. I just preserve the byproduct. That actually turned out to be the thing that made it so that abelian categories work very well. And in fact, in the work that I did with Michael Ching and Matthew Burke, this is in general a property of stable categories. So we showed that there's always a tangent structure, but when you restrict to functors between stable categories, it's always a Cartesian differential category for exactly this reason. So I'm not sure that that's fully answering your question, but this is kind of the key thing. That this now looks like exactly what the categorical differentiation people think of as linear. And in fact, there's a paper written by Robin Cockett and J.S. LeMay that show that when you have linearization, which is what this D1 is trying to do, that you always get differentiation.
So would you say that it's enough to have additive categories, or that complicates things in any way? Maybe exactness plays a role in taking homotopy, I don't know.
Yeah, so in abelian functor calculus, not all functors, of course, are linear. but you can always use the exactness property comes in to tell you what the difference is between something being linear and not being linear. So a reduced functor has the property that it's always equal to f of x plus f of y plus something left over, which we call the second cross effect. Now those cross effects are used to make the Taylor series in abelian functor calculus. So that's why I need it. I don't know what to do in an additive category, but I just haven't thought about it from the perspective of from the categorical perspective. I haven't thought about what I might do there. So it's possible that there's a way to work around that I just haven't thought of. But from the functor calculus perspective, it didn't make any sense. We needed the exactness.
That's very clarifying. Thanks.
Thank you.
Right, do we have more questions for Kristine?
You had another question? I raised my hand again.
Sure.
I wasn't sure if your hand was still up or if you raised it again.
Matthias's question sort of reminded me something about the stable versus the abelian things you said. So you've got like abelian functor calculus as a Cartesian differential category, and you've got the much larger thing of sort of the tangent category of
infinity functors.
Infinity categories, yeah. But then you've got sort of in between those the stable ones, right?
Mm-hmm.
And so what we were talking about here was doing the Fodor-Bruno stuff for the abelian categories. We thought about doing the Fodor-Bruno stuff with the stable things and what you get there.
Yeah, so I kind of hinted at this at the end that I'm hoping that we can, in the abelian calculus case turns out to be a really nice playground because everything just works. Like this property that I've written down underneath about the fact that f of x plus y can always be written down explicitly in terms of f of x plus f of y plus something left over. Like that makes things really, really concrete in the abelian functor calculus case. But I'm hoping that if we can get things working there, that we'll actually be able to go back to the full tangent category and try to understand what's going on with both the chain rule and operands there. So
I guess I wasn't thinking about the full tangent category, just the one restricted to the stable objects.
Yeah, so I think that what will happen is that if you restrict to the stable objects, whatever we do in abelian functor calculus will go through with no trouble. It tends to be the case that you can think about stable categories as like some version of chain complexes or some version of spectra. Everything tends to work exactly the same way.
I see.
So I don't think that there will be much of a difference between the abelian functor calculus result and the part about the stable categories result.
Okay.
But I'm hoping we can actually even do more and maybe understand a little bit more about what to do with what to do on the full tangent category or infinity category. And I don't know what that looks like yet. Michael Cheng and I had a conversation about this, and we think that there's maybe it will work. Maybe there's something to do there, but I don't know what it is yet. He might have better ideas than me.
Cool, thanks.
All right. Then unless we have a question for Kristine, maybe it's a good time to thank her and all the speakers again. And so tomorrow, let me just remind you that we start 1 hour later than today, so at 12 UTC -3. Right. Hope to see you all there.